Biology, and this is the paper solution of December 2017. This is for degree section, semester 3, second year, Mechanical and Automobile Engineering. So here I have divided this video into two parts, and this video will be covering from question number 1 to question number 4. As such, here I have not solved it completely, but I have given short answers, okay, or few points where you can elaborate the points or add your extra points. Okay, here it is only short answers to just give you the idea of the answer, but this is not the complete answer. For all the questions, I have also written the marks for which each question has been asked for. So let us start. Difference between steels and cast iron. So here I have written 2 points, but as such it is for 5 marks, so you have to write 5 points. So steel as such, it is having low carbon content, and cast iron, it is having high carbon content. Steels are less brittle, cast iron are more brittle. Question number 1b, that is the allotropic modification of iron, that is for 5 marks. Here iron is allotropic metal, so which means that it exists in more than one type of lattice, that is structure, that is BCC, that is body centric, FCC, that is face centric, depending upon the temperature. In normal temperature or the normal room temperature, iron is BCC, it is body centric in lattice arrangement, whereas at 910 degrees centigrade or Celsius it changes to FCC, that is face centric, and then at 1400 degrees Celsius it comes back to BCC again. The same thing has been represented in this diagram, that is BCC, okay, up to 910 degrees Celsius, and then it becomes face centric, and then again at 1400 degrees Celsius it becomes BCC. So BCC up to 910, then it becomes FCC, then after 1400 degrees Celsius, then again BCC. And it is shown that it is like alpha, okay, up to 910, and then after 910 it is delta. Okay, so this has been represented in this diagram. Okay, so you have to elaborate each point and also explain the diagram in detail. Here I have given you just the small explanation about the question. Then the classification of the material. So materials are of 3 types: metals, non-metals, and material combinations. Metals, it can be ferrous metal or non-ferrous metal. Non-metal, it can be ceramic or organic polymers. Materials combination, it can be composite like visco reinforced plastic, metal reinforced metal, metal ceramic, carbon reinforced rubber, ceramic polymer, or polymer cement concrete. Or it can be alloy, it can be ferrous alloy or non-ferrous alloy. So this was classification of material. Then question number 1d, that is mode of deformation in the material. So deformation is defined as the change of the shape of the body caused by the application of the force. So there can be 2 types of deformation. One is elastic deformation, one is plastic deformation. Elastic deformation is the deformation which appears with the application of stress and which disappears when the stress is removed. Plastic deformation, it is the permanent deformation which remains in the metal even after the removal of the stress. So you have to elaborate it more because it is for 5 marks. Then question number 1e, it is stainless steel and its classification. So first you have to define and explain stainless steel. So here I have written 1 line about stainless steel, that is the greatest advantage of stainless steel over the plain carbon steel and alloy steel is that it provides high resistance to corrosion in most of the environment and media. When we talk about classification of stainless steel, it can be ferrite SS, that is ferrite stainless steel, where the chromium content is from 12% to 27% and carbon content is 0.08% to 0.2%, and it contains structure that is ferrite phase, martensitic stainless steel. It is having chromium 12 to 18%, carbon 0.1 to 1.2%. It contains hard martensitic phase after hardening, austenitic stainless steel, where chromium is 16 to 24%, carbon is less than 0.2%, and nickel is 8 to 22%. So it is having the structure that is austenite. Then question number 2a, which talks about define critical cooling rate, describe various cooling curves on TT diagram for eutectoid steel and discuss the transformation. This is for 10 marks. So what I have done here, I have defined critical cooling rate, which is defined as the lowest cooling rate which produces 100% martensite with minimum internal stresses and deformation. So critical cooling rate, that is CCR, is defined as the lowest cooling rate which produces 100% martensite with minimum internal stress and distortion. So here, as you can see the curve, on the x-axis it is time in seconds and on the y-axis it is temperature. Depending on the rate of cooling, different type of grain structure can be formed. As you can see, when we talk about this curve, which you can see here, which is having a nose, it is the main part of the figure, and then depending on the different rate of cooling, you have annealing, as you can see, number 1 and 2. So when at this particular temperature or the rate it is cooled, then we have the perlite, which is coarse perlite and fine perlite, and then we have this normalizing, and then the curve number 4, which is missing the nose and going to the right side of the nose, and then the curve number 5, which is the CCR, that is critical cooling rate. So then 100% martensite can be formed, and then curve number 6, as you can see over here, and then 7, which is also having a temperature, which is held for some time, and then again it is cooled further. So it is austempering, it is called as. So as you can see here, different processes have been shown: annealing, normalizing, and then austempering. And at various temperature or cooling rate, perlite and bainite can be formed, and at certain particular cooling rate you can have coarse perlite, in these temperature ranges, fine perlite, upper bainite and lower bainite. And as you can see over here, we have capital A, which is austenite, and here as you can see, that is martensite, and in between you can see A plus M, that is austenite plus martensite. Here you can see MF, and here you can see MS. So here also you can see on the left side PS, and here PF, that belongs to perlite, and this is BS and BF, which belongs to bainite, and in between as you can see perlite, and this is A capital, that is austenite. So here in between, as you can see, it is A plus P, and here you can see A plus B. So this is the critical cooling rate, that is CCR, and this diagram is called as continuous cooling transformation diagram. Second year degree section. This is for mechanical and automobile engineering, and the subject is material technology. So in the earlier video we have completed up to question number 2A. So in this video we will be doing question number 2B and further questions. So explain the property and microstructure changes occurring during cold working and recrystallization annealing of metal. So let us start. Here we have to see the properties and microstructure changes occurring during cold working and recrystallization annealing of metals. So as such, Cold working is the process in which the metals or the alloys are heated below recrystallization temperature. So, the effect of cold working is the hardness, tensile strength, and internal stresses and electrical resistance increase, whereas the ductility and the corrosion resistance decreases. Annealing is the process in which the metal is heated at any suitable temperature for 1 hour and cooled it to room temperature. So here now we will be seeing the property, okay, and the structure changes during annealing heat treatment. It is like phases, it is recovery, recrystallization, and grain growth. Okay, so here both cold working and annealing is plotted. Okay, so when we talk about property during cold working, as you can see, the properties, that is hardness, tensile strength, internal stress, electrical resistance increase, whereas the corrosion resistance and ductility decrease. And you can see the grain structure, how it looks. Okay, so during recovery phase, what happens and recrystallization and grain growth, let us see. First we will read out the theory regarding recovery, recrystallization, and grain growth. During recovery, all the imperfection or the defects are eliminated completely from the metal. In recrystallization, nucleation is obtained and growth of new grains without phase change. Old distorted grains are replaced by the new stress-free, strain-free grain. Next is grain growth, that is small grains grow still smaller and are finally absorbed by the larger grain, which grow still larger. So now we will refer to the diagram. As you can see, cold working, there is structural changes. Then during recovery, all the imperfection, okay, are removed. And if you can see, during crystallization, nucleation is taking place. Okay, so after that recrystallization, we will have stress free and strain free, okay, grains. Then in grain growth, the smaller grains are further becoming smaller, okay, so that it is absorbed by the larger grain and they further grow in size. So the grain size increases. So this was, and as you can see, the hardness, okay, as we go through the recrystallization phase, the hardness, tensile strength, internal stress, electrical resistance decreases, and when we go to the recrystallization phase, the corrosion resistance increases and ductility also increases. So now question number 3a, okay, here I have not drawn the equilibrium diagram, that is Fe3C diagram, because that you must be already having and you must have already studied, but still if someone wants, please send comments or request. So question number 3a will also be solved or answered. Question number 3b, describe, okay, and one more thing which I have mentioned in my earlier video, that this is only few points. There are more points available in various test books that you can use, and also the points which I have written are very short. You have to elaborate during writing the answer, because these questions are for 5 to 10 marks, so you have to write more. Okay, like for example 5 marks you have to write around 1.5 page or 1 page. For 10 marks you have to write 2 or 2.5 page, depending on the content which you have to put, and also you have to draw diagram wherever applicable. So now describe the cooling of 0.5% carbon steel to room temperature. Also find out the proportion of micro constituents in it at room temperature. The steel containing 0.5% carbon, as it is cooled below upper critical temperature, the iron begins to change the FCC structure, that is face centered, to BCC, that is body centered structure. Okay, so and the constituent are obtained during microstructure changes at room temperature are perlite and ferrite, 60% perlite and 40% ferrite. So this was question number 3b. And now let us go for question number 4a. What is fatigue of metals? Explain the method of testing the metal for fatigue. Discuss the various methods used to increase the fatigue life of a component. The maximum stress that a material can withstand without failure for a specific large number of cycles of stress is termed as its fatigue or endurance limit. Method of testing the metal for fatigue. Rotating beam fatigue test machine. As you can see over here, there is a motor, okay, for rotating, and there are bearings, okay, and the holder, and as you can see there is a test specimen, okay, and there is a revolution counter, okay, which reads the number of cycles. So the revolution counter reader provided with machine records the number of cycles applied, and when the specimen breaks, then the counter automatically disengages. So it counts the number of rotation, okay, or revolution of the test specimen before it breaks. Now regarding how to increase the fatigue life of the component, here I have mentioned two methods, but there are other methods also, and here I have mentioned only a short point. You have to elaborate. Corrosion. It reduces the number of cycles required to reach for every stress amplitude, okay. Here we can protect steel against salt corrosion by chromium or zinc plating. Surface finish. Scratches, dent, identification marks can act as stress razor and reduce fatigue properties. Short pinning a surface produces surface compression residual stresses, and it will improve the fatigue performance. So these are only 2 points to increase the fatigue life of the component, but there are more points. Now question number 4b. What is hardenability and what are the factors affecting hardenability? Explain Jomini and quench test. Hardenability is the ability of the steel to develop its maximum hardness, that is depth of hardness, when subjected to normal hardening and quenching cycle. The factors which affects hardenability, there are various points I have mentioned here too. Alloying elements. In steel, alloying elements increases the hardenability. Severity of quench. Oil quenching increases hardenability as the cooling is slightly slower than with water or brine water. Now regarding Jomini and quench test. So here I have drawn the setup, how it looks like, but only a part of the setup, okay. So here as you can see, there is a specimen which is heated to austenizing temperature and kept in the furnace for proper soaking time. This specimen, the diameter is 1 inch, okay, and the total length is 4 inch, and the orifice ID from where the water spray is coming is half an inch, and the distance between this water source and the specimen is half an inch, okay. So the water is at 75 plus or minus 5 degree Fahrenheit. So then after the bar has been cooled, one band is ground from collar end up to the quench end and polished for proper hardness test. The hardness is measured on the Rockwell hardness tester with RC scale. So as you can see in the next here, this is the complete specimen, okay, and this is the on the left side the quenched end and on the right side the collar end, and it is ground and it is divided into 16 sections, okay. So as you can see, 1/16th section, because the total length is 4 inch, which is divided into 16 sections. So 1/16th of the section, then 2/16th of the section, because at these places the hardness will be taken, okay, and we can draw the hardenability curve. If we want to find, for example, 50 RC at what depth, okay, or from the the specimen, because it is cooled at the bottom, that is the quenched end. So from there, what length, okay, or the distance from the quenched end you can achieve a particular hardness. For example, 50 RC if you want to check at what depth, okay, or the distance from the quenched end you have achieved this 50 RC, you can plot it, okay, and drop down, and you can find the distance from the quenched end where you have achieved this 50 RC. So this is hardenability curve. Today's topic of discussion is the paper solution December 2017 for the subject Material Technology for Mechanical and Automobile Engineering degree section, semester 3, second year. From question number 1 to question number 4 of December 2017 of Material Technology has been uploaded in the earlier 2 videos. This is the third video. So here we have taken question number 5. Discuss any one of the case hardening method in detail. So hardening method, that is secondary hardening, the development of very high strength level in many alloy steel is achieved by secondary hardening process, which is a type of precipitation hardening reaction. As the alloy steel contains several carbide forming elements like MO, CR, W, etc., therefore the hardness is maintained constant up about 400 degrees centigrade, up to about 400 degrees centigrade, but afterward, as the tempering temperature increases, the hardness also increases due to precipitation of fine carbide particles. As you can see over here, the hardness, okay, is constant up to about 400 degree Celsius. Okay. Now, but afterwards, as the tempering temperature increases, the hardness also increases due to precipitation of fine carbide particles. But after 550 degrees Celsius, the hardness value decreases sharply due to the breakdown of coherence and coarsening of carbide particles. So as you can see over here, at around 550 degrees Celsius, okay, after 550 degrees Celsius, the hardness value decreases sharply due to breakdown of coherence, okay, and coarsening of the carbide particles. So this is the figure of tempering curve for alloy steel, that is secondary hardening. So this is the curve. Up to 400 degrees Celsius it is constant, the hardness, and then it rises up to 550, then the hardness starts decreasing. Now question number 5b. What are the smart materials? Discuss a few applications of smart materials. Smart materials like soft solids and solids under condition in which they respond with plastic flow rather than deforming elastically in response to an applied force. This is applicable to the materials that have complex microstructure such as polymers, glass forms, body fluids, etc. Now, question number 6a. Okay, just to bring to your point, or just to remind you that the questions which we are discussing over here, we are only covering few points. Details are not given over here, so you can add your own points from your notes, or you can elaborate the points which I have given, because the questions are asked for 5 to 10 marks, so therefore you have to write more. Write short note on nanomaterials and their synthesis route. Nanomaterial constitutes component that are smaller than 100 nanometer in at least one dimension. Two approaches for manufacturing of nanomaterials, that is top-down approach and bottom-up approach. In top-down approach, breaking down of large pieces of material to generate required nanostructure from them. Bottom-up approach, single atoms and molecules are assembled into larger nanostructure. Then question number 6b, okay, that is write short note on creep behavior of metals. So as you can see over here, okay, this is primary creep, secondary creep and tertiary creep. This is the strain as a function of time due to constant stress. Primary creep, strain rate is relatively high but decreases with the increasing time. Effect of work hardening is more than of the recovery process. Secondary creep, the rate of work hardening and recovery during this stage are equal, so the material creep at steady rate, minimum creep rate. Okay, as you can see over here. Tertiary creep. Creep rate increases with time until fracture occurs. In this stage, tertiary creep can occur due to knacking of specimen or grain boundary sliding at high temperatures, and this continues till the specimen fractures. So as you can see over here, it goes up. Okay, so tertiary creep can occur due to necking of specimen or grain boundary sliding at high temperature. Okay, so this was regarding creep, and let's go to the next question. Question number 6C. Write short note on dislocation and strain hardening. Dislocation. The presence of extra atomic plane or absence of an atomic plane results in formation of dislocation. As you can see over here, this dislocation which is traveling. So as the moving dislocation moves, their density increases. If the moving dislocation comes across any obstacle, the movement is restricted, requiring more stress for their movement. Dislocation moves forward by leaving a loop. As you can see, loop is formed. So dislocation is moving forward, but it has left a loop. Dislocation moves forward by leaving loop around the obstacle. Then strain hardening, because this question is about dislocation and strain hardening. Strain hardening, ductile material increase in strength and hardness when plastically deformed at temperatures lower than the crystallization temperature. This is called as work hardening or strain hardening. So as you can see over here, resolved shear stress, and this is the shear strain, stage 1, stage 2 and stage 3, and this is the figure for work hardening or strain hardening. So the stage 1 which we have seen over there, okay, so easy glide region, very little strain hardening in crystal and dislocation are able to move relatively large distances without encountering any obstacles. Stage 2, linear hardening region, curve is almost linear, indicating strain hardening increases rapidly. Stage 3, parabolic hardening region, the rate of strain hardening decreases, the stress are very high so that the dislocation struck up in stage 2 are able to move. Now question number 6D. Write short note on isomorphous phase diagram. This type of phase diagram is loop type and occurred for two metals. In below diagram, C and D are melting temperature of metal A and metal B respectively. As you can see over here, this is C and D, that is the melting point of metal A and metal B. So this is the solid phase, this is liquid phase, and in between solid plus liquid. So this is the phase diagram. So now regarding question number 6E, write short note on retained austenite. In conventional hardening, steel are heated to an austenitic phase and quenched to room temperature to produce hard martensite phase. So due to incomplete transformation, some austenite is retained at room temperature. Retained austenite are very soft and ductile, due to which the overall hardness of the steel is reduced. So as you can see over here, this is martensite and retained austenite, which is the white patches. Okay, so this was retained austenite, but you have to go and put some extra points and elaborate the points, because the questions can come for 5 to 10 marks. So this was the questions for material technology subject for December 2017 paper solution. So we have covered all the questions, and only one question, that is iron carbide diagram, okay, that is equilibrium diagram, is not covered. If you want, please comment, then that diagram also will be made or provided to you. Hope you like the video. We will again meet in the next video very soon. Till then, goodbye.